Hi everyone, welcome back. In this lesson we'll be talking about some of the rules of calculus. Now, if you remember, when you learned arithmetic, you realized that you had to do certain things differently when you're using multiplication. For example, if you're multiplying 13 times 15, you can't just say, well, let's multiply the first digits and then the last digits and combine the result. No, we realized that we had to do kind of this cross multiplication, right? We need to break things apart, multiply the pieces, and combine them back together. And there's something similar for the rules of calculus. If we're trying to take the derivative, or like the changing pattern, if we're trying to take the derivative of a pattern, and that pattern has little subpatterns, we need to be careful about how we're putting it all together. So in the next few lessons, we'll be talking about a few different interactions and just how they result in changes. And we just want to make sure to account for the right things. So let's get started. Addition is probably the simplest one. Now, I like to imagine a scenario, let's say building a fence. You have two friends, Frank and George, and they're each contributing to the fence. Maybe Frank is getting the wood and George is getting the paint. And now the total cost of your fence will be the wood cost plus the paint cost. So in this case, the total is Frank's cost and George's cost. Now when we take the derivative, what we're saying is, for every additional foot that I ask for, how much does the cost go up? Well, in this case, it's actually, we can kind of take this equation here, t, the total, equals Frank's plus George's cost. We can sort of differentiate the whole thing with respect to x. And again, what that's saying is, I want to know the pattern of changes that I'll see in the cost, but write it in terms of what we're seeing with Frank's cost and George's cost. And this kind of makes sense where we'd have this addition where we say, every extra foot of fencing, well, Frank has to buy his extra foot, and George needs to buy his extra foot. So the total cost is just that accumulation. And so this is a very kind of basic, straightforward scenario, and we can work it out the old-fashioned way too, right? We can take the original, we can take the new amounts, we can subtract them, and see that the difference is just the added difference of the new material. One little shortcut is just to kind of write functions with just f and g instead of writing out the whole f of x and g of x, just because we're trying to see the relationship. So we can write f of g prime, and what that prime symbol means is the derivative, because it's, again, the kind of simpler version of the derivative, just to kind of see the rules. So we can say f plus g prime equals f prime plus g prime. And again, it sounds kind of cumbersome when we say it out, but the idea is just to say, okay, if we have two pieces that are being added and we want the total change, well, it's just the change from each part. And that's something that intuitively we probably could figure out as well, right? If you have two pieces that are both contributing to a whole and you want to know how the whole changes, well, just look at the contributions from the parts. Okay, now let's hop into something a little bit more complicated, which is multiplication. We might have our two friends that are building kind of our square garden like before, except this time it's not necessarily a square, it could be a rectangle. So Frank could be moving like this, and George is moving up like this. And notice that Frank is actually moving further than George with each step. Now the question is, when they each move forward, what's going to happen? How much extra area are we getting? And we can kind of work it out like before. So we come down and we see that, okay, similar to a square growing, we have this rectangle that's enlarging. The g part, George, he'll take a step of dg. Frank will take a step of df. Now with each instant, or with each kind of change in our system, it might turn out that Frank is actually moving further than George. So in this case, we're getting a little bit more here than we would be up here. But the same kind of approach applies. We have our sort of individual contributions, and then we have this kind of interaction. And if you remember, this interaction is not really real. It's something that's on the graph, but in fact, in reality, when we're kind of changing our system, we only have these kind of side pieces. This is kind of an artifact of our measurements. So when we do it all out, we sort of get these two pieces as the result. So every time we change, we're sort of adding on these little strips here with this kind of artificial piece being thrown away. And what it looks like at the end of the day is like this. So f times g, the derivative of that is f times the derivative of g plus g times the derivative of f. And again, f times the step in g plus g times a step in f. And so again, this is just saying when we have two pieces that are multiplied and we start wanting the pattern of steps that they take, well, this is the pattern that we get. And so, one other kind of insight is that it gets a little bit confusing because we're talking about f and g changing, and I'm not really sure how, right? Because these are different variables, and where's the x involved? I like to imagine x is kind of like a timer or something happening off in the corner. And every time x changes, g and f change as a result. So maybe the timer is going off every second, and every second f and g are taking different changes. So again, x is this sort of, if you want to go to the x level, x is this kind of, you consider it a timer or just sort of a parameter or a variable, which is off in the corner changing, and both of these systems are changing as a result. Eventually, if we like, we can put things back in terms of x, but just for now, we're just trying to see the interactions at the f and g level. So this is what it looks like. F times g, the derivative of that is f times the derivative of g plus g times the derivative of f. And again, you want to sort of visualize this. So imagine this rectangle growing, throwing out this piece that doesn't really exist because there's an interaction, and just measuring these two changes. Okay, now let's go to the next one. And this is sort of, it's a tricky example, but I kind of like it because I think it's a little bit useful. We're going to talk about simple division, basically inverses. So instead of x, we're going to have 1 over x. And the question is, now how does that change? And it's a little bit weird to think about because 1 over x, it's an inverse. So the bigger x gets, the smaller 1 over x gets, right? Because as x is getting big, it's being divided into smaller and smaller pieces. So let's just take a very simple example. Let's say that you have a cake and you're sharing it with Frank. So it's this cake, and it's just you and Frank, and you decide to cut it down the middle. So you're cutting it, and then George walks in. Oh man, I forgot about George, and he wants a piece. So how do you share this cake with George now that you've already cut it with Frank? You're kind of stuck. Here's a solution. Basically cut it again, but cut it into thirds. So you've already cut it into halves. Cut it again into thirds, and give the newcomer one piece. So everybody cuts their existing part into 3 pieces, and gives the new guy one of their pieces. So you're A, you cut your cake into 3 pieces and give George one. And Frank, who's already there, he was B, he cuts his cake into 3 pieces and gives George one. And at the end of that, everybody has equal amounts. Because the new guy got 2 pieces, I have 2 pieces, and then Frank has 2 pieces as well. Sorry, some of the names are a little confusing. But the idea is that if you take your existing amount, cut it again, and give one of those portions away, now the new guy can sort of have his share. And this works. Let's say there's a 4th guy that comes in, a 5th, a 6th, a 7th. Each time it happens, each time someone comes in, everybody takes their share, cuts it up, and gives away a piece. And that sort of tracks the 1 over x growth. Because basically 1 over x is saying you have a whole and you're dividing it into x parts. And we're trying to see, well, how does my share change over time? And so what's going to happen actually is that if I have a share of 1 over x, and the new guy walks in, we're basically going to lose, so it's a negative sign, we're going to lose 1 over x plus 1, because when there's 2 people, I lost a third. When there's 3 people, I lose a fourth. When there's 4 people, I lose a fifth, and so on and so on. So basically this little equation here, negative 1 over x times x plus 1, that tracks how much I will lose with every step. Every time someone else comes in and I have to redivide my cake, that's how much of the total that I'm going to lose. Because in the case of 1/2 and 1/3, I'm actually losing a 1/6 of the total. So I had a half. I'll be going to a third after this is all done, but in order to do that, I had my half and I lost a 1/6, and that's how I got to a third. So it's a little bit of a tricky scenario, but I just like to imagine a cake, and that helps me kind of get my head around it. Now what happens though is that little step of 1 is actually kind of dependent on the size of step that we took. It's that dx, it's that measurement artifact, right? When we went from x to x plus 1 people. And so the next step is to actually make that perfect. And so when we make it perfect, we actually lose 1 over x squared. And that's the kind of ideal amount that, we say in the limit, with perfect numbers, with perfect decimal, with infinitely small slices, that's the amount that we're losing. And there's a few examples in the post where you can sort of walk through it. So with that, we've walked through the high-level intuition behind some of the beginning rules of calculus. Happy math.